Thank you, Christian, again. So this result, we introduce something that's called internal differential boomerang distinguishers, which is kind of a new technique of analysis. It is a combination of internal differential attacks and classical boomerang attacks. And with this new type of distinguishers, we target the permutation of Keccak, and we give very practical distinguishers on round-reduced Keccak. For example, on 6 rounds, we give a distinguisher with complexity 2 to the 5, and on 8 rounds, 2 to the 18 only. So it's completely practical. We were able to confirm this on a computer. So to understand what's internal differential boomerang attack, first we have to know what's internal differentials and what's boomerangs. So let's start from the beginning with internal differentials, which were introduced by Thomas Perrin in the analysis on the compression function of Grostel. So in classical differentials, you work with a pair of states, and then you investigate the propagation of difference between these two states through the rounds of the primitive. In internal differentials, what you do is you split the state into 2 halves, and then you investigate the propagation of the difference between the 2 halves of the state. So it's quite original idea, and what Thomas noticed, because of the way Grostel was built, so basically inside you have already kind of 2 states, and they operate on very similar permutations. So basically he was investigating the propagation of this difference initial between 2 states that he fixed through the rounds of these 2 permutations. The same technique, and also very original, was applied to Keccak by Dinur, Dunkelman, and Shamir. But in Keccak, you don't have this nice division into 2 states. There you have 25 words. So what they did is they took each of these words, which is 64 bits, they split into half, and then they took as an internal difference the difference between the first and the second half of each word of the state. Okay, so it's similar idea, but kind of still very different and very original. So they applied this thing to Keccak because they noticed that in Keccak the round constants have very low Hamming weight. Okay, so this is the internal differential attack. Now let's take a look at boomerang attacks. But boomerang attacks are far more familiar technique of analysis. You have this primitive, let's say block cipher. You regard the primitive as a composition of 2 permutations, F and G. You find 2 characteristics, one for the first part, for the F permutation, one for the G permutation. And then you launch the boomerang. So how you launch the boomerang? You start with a pair of states that have some difference delta according to the input difference of the first characteristic. Then you go through all the rounds. You produce a pair of ciphertexts. You XOR the Nambla difference according to the Nambla difference of the second characteristic. You go up, and here you expect the difference will be delta with probability p squared q squared, where p and q are the probabilities of the first and the second characteristic. So why this happens is because if this pair of states follow this characteristic, and then we go down and these 2 follow this characteristic, so if you have delta star, here Nabla star, then here you're going to have delta star, and then when you go up according to this characteristic, here you'll have delta with probability p. So basically I have these 4 trails. I have 2 different trails, and each of them have to pass twice. So Wagner applied the boomerangs initially to ciphers, so secret key primitives. Later these were adapted to the case of hash functions, and there actually have more freedom because of the message modification, and because you can start the boomerang at any place. For example, I can start the boomerang in the middle. I can fix some state here and XOR these 3 differences, obtain the other 3 states, go here up, go down, and I can obtain the 4 input states and 4 output states. The main point of the boomerang is production of this boomerang quartets. So 4 states that have some XOR difference on the input and XOR difference on the output. In the case of hash functions, I can use message modification because of the freedom, as I said before. Actually, I can pass several rounds. So this is called a boomerang switch here in the middle. I can pass several rounds around the boomerang for free when I control the states and I use message modification. Okay, so that's the boomerang attack. We know what's internal differential. We know what's boomerang. Let's take a look at what's internal differential boomerang attack. Okay, it seems my figure it's it's gonna be hard to explain. Okay, let's try to explain. So again, I split my cryptographic primitive into two parts. I have F and G. So for the first part, I'll be building internal differentials. For the second part, I'll be building standard differentials. The main difference between the internal differential boomerang and the standard boomerang, in here I work with 2 pairs of inputs, unlike in the standard where I work with 4 pairs of inputs. So I start, so imagine this is my internal differential, this is my standard differential. So I will start with a pair of inputs, with one input that has internal difference delta. I will go down through the first several rounds, then I'll go completely down. Once I reach here, I'm gonna XOR this difference, go up, go completely up, and here I claim that I'll receive internal difference delta. Why? Because at the boomerang switch, same trick is applied there. Because here I have delta and delta star, and here I have this symmetric difference. Here I'm gonna obtain this delta with probability. Now I have probability p square q, sorry. Why? Because I pass twice the internal differential part and I pass only once the standard differential part. So this technique, it's very nice when you can find a good internal differential for some part of the cipher, for the top or the bottom part. Okay, so now we have the technique, and let's try to apply to Keccak. Well, actually, we are applying to the permutation of Keccak. I think we all know what's Keccak. It's the winner of the SHA-3 competition. It's the new SHA-3 standard. It's based on the Keccak permutation. Actually, it's based on the sponge construction, and it relies on the Keccak permutation. So the permutation operates on a state which can be seen as 3-dimensional array. It has 25 words, and each word can have different size depending on the version. We're going to analyze the version that has 64-bit words. So you have 25 64-bit words. It has 24 rounds. We'll be analyzing round-reduced Keccak. So this analysis cannot be applied to the whole Keccak. So this is the state of Keccak. It has something that's called rows. It has something that's called columns, slices, lanes. Each round of Keccak is composed of 5 transformations. The first 3 are the linear transformations. Then I have 1 non-linear and only 1 round-dependent transformation. The first is the linear transformation, theta. It has very good diffusion. In forward direction, 1-bit difference expands to 11-bit differences, and in the backwards direction, it has even better diffusion, because usually 1-bit difference expands to around half of the state bit differences. The second one just rotates the words within each lane. The third one moves the lanes around the state. The fourth is the only nonlinear operation chi operates. It's a 5-bit S-box. And the fifth one is the only round-dependent operation. It's just XOR some round constant. The main point is these round constants have very low Hamming weight. Because of the low Hamming weight, we can find good internal differentials on round-reduced Keccak. So design of Keccak relies on this hermetic sponge strategy. In the security proof, they say, okay, Keccak is secure as long as the permutation has no structural weaknesses. So with this work, we try to point out that perhaps 8-round reduced Keccak has some structural weaknesses. So we'll be applying the internal differential boomerang to Keccak. For that reason, first we have to find internal differentials. We have to find standard differentials, concatenate them, and launch the internal differential boomerang distinguishers. We'll be launching on 6, 7, and 8 rounds of Keccak. So first, let's try to find the internal differential characteristic. First, let's give an example of 3-round internal differential characteristic. Let's make it clear this idea of how to build internal differential is all due to Dinur et al. Okay? So we're just trying to follow a little bit their approach, a little bit something else, but it is their idea in practice. So imagine I want to create an internal differential characteristic on 3 rounds. What I do is I start here just before the addition of the round constant with 0 internal difference. So in each word, the first half and the second half coincides. Now if I go forward, after the addition of the round constant iota 1, it has Hamming weight 3. I'm going to get the internal difference of 3. Then after the linear layer, it will expand to 33. And then I'll have a non-linear layer. And actually, I don't care about the output difference of the non-linear layer, because as we will see, this round here can be passed with a strong message modification. Okay, so if I start here from 0, I only care what's the difference here just before. And then if I go backwards, because the internal state difference is 0, these operations will keep it 0. I'll come to the round constant addition. It will reduce only 1 bit difference. Then I'll have the S box here. I'm going to pay probability to the -2 to keep the 1 bit difference. And then the linear layer will transform this difference into difference in 429 bits. So I'll have 429 ones, and the remaining bits will be zeros. So this is the 3-round internal differential characteristic. Actually, I can do 4 rounds, but if I start from the original round 0 of Keccak, I cannot do 4 rounds. That's why my first round is the round 3 of Keccak. So again, I start with some 0 difference just before the round constant here. I go forward direction. The round constant here has Hamming weight 2. Linear layer expands to 22. I come to the non-linear layer, and I say I don't care what's here because I'm going to use message modification, as we will see later. If I go backwards, this round constant introduces difference in 5 bits. I pay 5 active S boxes here to keep it 5 bits. The non-linear layer will make this difference in 397 bits. This round constant increases by 1 bit. And here is the funny part, here is the interesting part. Here I'll have maybe all 320 S boxes might be active, but we found with experiments that with probability 1, if I have these 398 active bits here, then even after the nonlinear layer, I can determine the difference in 64 bits with probability 1. So some particular 64 bits will have some particular values with probability 1. So actually here I don't pay any probability. Here I don't pay any probability because I'm going to use message modification. The only thing I pay is here 5 active S-box. But with another set of experiments, we found out that here there is some differential effects. So instead of 2 to the minus 10 for 5 active S boxes, the real probability is only 2 to the minus 4.6. Okay? So these 3 and 4 round internal differential characteristics will be used in the Boomerang. Now let's take a look at the standard differential characteristics. They're based on something that's called parity kernels, which allows to go one route with very low Hamming weight. So here I start from here. I start with 4-bit difference. After one round, I still have 4-bit difference. Of course, I have to pay for these 4 active S boxes. After the linear layer, I'll have 44-bit difference. And here is second trick we use. We consider only truncated differences. So actually, we don't pay at all for this active S box. We consider truncated differences. And then we went one additional round. And again, with experiments, we found out that the difference will be determined in 118 bits with probability 1 without paying anything for the active S boxes. So this trail here, it's quite cheap. I pass kind of 2 rounds for free. In the backward direction, I only fix the difference here. And in this nonlinear layer, I'm going to use the message modification to pass it deterministically. Okay, so now I have my internal differentials. I have my standard differential. I can launch my internal differential boomerang attack. So how it works, I already talked about the message modification. So with the message modification, I'm trying to pass the nonlinear layer of the last round in the internal differential trail and the nonlinear layer in the first round of the standard differential trail. The message modification is quite complex. I'm not going to explain what's there, but what I found out, and I think it's what's kind of interesting, is that it's much easier to launch attacks that have infeasible complexity than real-time attacks. We found these nice trails, internal differential, standard differential. We were like, okay, let's try to implement this on a computer. We start implementing. It doesn't work as expected. In Boomerangs, you can have contradictions very easily. Now, this is the third time it happens to me. I had 2 more results previously where I tried to launch the Boomerangs in practice, and it didn't work as expected because of these contradictions. So you have to be actually very careful. I think there are plenty of boomerang attacks out there which are not actually correct. Because when you're launching some theoretical attack, you don't even have to implement in practice, and you're just saying, okay, this is good. I found this trail, that trail. I can launch my boomerang. In practice, it doesn't work this way. So we had a lot of problems here. And actually, we found several standard trails. None of them worked. We had to change. And after some time, we were able only then to launch the internal differential boomerangs. Again, we use heavy message modification. We were able to pass 2 nonlinear layers. We were able to find some neutral bits, meaning that if I change the value of these neutral bits, still I pass these middle 2 rounds for free. So how we launch the internal differential boomerangs? We start from the middle. These 2 nonlinear layers in the middle are passed for free because of the message modification. And then I use my neutral bits to go backwards through these rounds and find input difference that has the same internal input difference, go forward, find the output difference, produce the boomerang pair. So again, the main difficulty was this message modification in the 2 middle rounds. Why? Because if you take a look at the real probability of the boomerang, it was exceptionally low. I get for 6 rounds 2 to the minus 40, for 7 rounds 2 to the minus 48. If I start from round 3, I get a bit higher, but still it's exceptionally low. Because these 2 middle rounds have very low probability. But because we were able to pass them with a message modification practically for free, the complexity of producing this boomerang pair, it's very low. So basically for 6 rounds, we were able to do it in 2 to the 5, and for 8 rounds in roughly 2 to the 18. Only because of the strong message modification. So to conclude, internal differential boomerangs might penetrate more if the primitive allows the construction of internal differentials. We have shown practical distinguishes on 8th round of Keccak using these internal differential boomerangs. Let's make it clear, this is only for the permutation. The hash function, we don't have any claims regarding the hash function. We cannot attack the hash function. We are only analyzing permutation of Keccak. And of course, there are some open problems, the main one being, can you extend to more rounds, more than 8, but keep it practical? Because maybe you think you can extend, but then in the middle there is some contradictions, and you didn't predict this thing. And that's all, thank you.
Thanks again, Ivica, for the excellent talk. Do we have questions for Ivica?
There is no key in Keccak, right?
Sorry, I cannot hear.
There is no key in Keccak.
There is what?
No key. There's no key in Keccak, right?
There is no key, yes.
Yes. So what does it mean to have a distinguisher on a function which has no key?
As usual, when we try to justify this type of distinguishers in the open key settings, we think that maybe somebody will use this Keccak permutation in another setting, but this might come to...
Okay, so let's say it differently. So here you have propagation of differences, and I remember that the previous speaker says that to look at the propagation of differences, it goes well when you have Markov cipher. Here you don't have any Markov sinks, you don't have any random sinks, so the function is completely deterministic. So are the probabilities of propagation of differences making sense now?
We try to see if this round-reduced permutation of Keccak can model some random permutation open key. In a random permutation, we say, even if everything is open, can you really produce this thing? Probably not. The thing is, this is still an open problem, as you might know. Still nobody can prove if this open key is important or not, or how to formalize this. So I cannot say more than this. We're just trying to compare intuitively to some random permutation open key. And we say, okay, in the random permutation, we cannot produce this. In round reduced Keccak, you can.
Any more questions for Ivica? Thomas?
Thank you. You were saying that you didn't try to extend to more rounds because it didn't become practical and you might have some contradiction in the middle.
Yes.
I was just wondering, let's say that you forget about the contradiction, how far can you go?
We haven't tried. We thought we have to go practical. We really haven't tried. Because even if we try one more round, we were not able to extend. And our target was only practical distinguishes for the round reduced.
Do you think you could apply this idea to smaller versions of the Keccak permutation so that X might be practical for more rounds?
I think for smaller version, actually, it will be practical for less rounds because the diffusion goes faster there. The word size is smaller.
Diffusion does.
So I suspect it's going to be less, or maybe 8, but I don't think it's going to be more.
So the Keccak permutation is also used in other primitives, like for authenticated encryption.
That's secret key.
But I mean, your probabilities that you have 2 to the minus 100, that could still be good enough to violate some security claims in that kind of use cases, no?
Perhaps. The thing is, we have to control completely the input. You know, in these authenticating encryption schemes, you actually don't control the full input. You know, you can just XOR certain number of words each round, and here we have to control completely the whole input. So maybe it will not work, at least not for now.
Okay, any more questions? Otherwise, join me in thanking Ivica again.